Hey Ramesh, let's build something.
Okay, so let's build a DAC. Remember what a DAC does. A DAC is a digital to analog converter, which means when I have my microcontroller produce a digital value, we write to the DAC and the DAC produces an analog value. So maybe it produces one particular value on a signal, some signal. So we want to see how to do this, and we will do this by building a circuit for it. There are two designs that we can do for the analog circuit. One is a binary weighted circuit. The other, which is more popular in systems, is an R2R ladder circuit. The binary weighted design is intuitive, so we will do this first. So our goal is to produce a signal. So we said if let's say we're working with a 3-bit DAC, which means that I have 7 levels. So our precision, so we have 3-bit DAC, we have 8 levels, and the 8 levels are from 0 to 7, and we are going to write that down here: 0, 1, 2, 3, 4, 5, 6, and 7. And we want to produce a voltage, and let's assume our voltages are between 0 and 3.3 volts. So we want to produce analog values. This is our digital, and we want to produce an analog value V out, which ranges between 0 and 3.3 volts, where each of these then will be a fraction of that. So this will have a value of 1. So it will have a value of 3.3 times 1 over 7. This will be 3.3 times 2 over 7, and so on. So when we get here, it will be 3.3 times 7 over 7. That will be my voltage. So that's my behavior that I want to get.
So what's the resolution of this DAC?
So as we see, the smallest change we can capture is a difference between consecutive values, which in our case is 3.3 divided by 7. So our resolution delta is 3.3 divided by 7. And our precision again is 8. So that's the design we are looking for. So let's design this. So again, here is our schematic microcontroller and we're going to use 3 bits. For now, it doesn't matter. I'm going to call them bit 2, bit 1, bit 0. So this is our bit 2, bit 1, and bit 0. So we're going to use the 3 bits, and we're going to produce our output, which is going to be our V out. And the way we're going to do that is we're going to connect resistors, and we make an observation that each of these bits, this bit has a position of 1, this bit has a position of 2, and this bit has a place significance or place value of 4. So when we choose our resistors, we will choose them in that ratio, which is 4:2:1. So we will use the bit 2 will have 11K, we'll have 22K here, and this will be a 44K.
So each one's twice as much as the other one.
So the bit 0 is, remember, the bit 0 has a place value of 1. So the resistance, that is whatever signal comes out of here for a 1, has half the significance as bit 1. So in order to do that, we subject it to a higher resistance. And so the lower the significance, the higher the resistance. So bit 2 is the highest significance, so it has the least resistance, which is 11K. And notice the ratio between these three is 11:22:44, which is 1:2:4, which is exactly what we want. So let's analyze this circuit to see how it behaves. So let's take our table again. This is our N. This is the bit values, and I'm going to represent them by Q2, Q1, and Q0, which is basically what I see here, Q2, Q1, and Q0. So if I have a 0, this is a 0, 0, 0, and this is my V out. Now, if I have an N value of 1, then what I have is this is 0, 0, 1, which makes this a 0, this a 0, and this is a 3.3 volts. I'm going to make, because I have a 1 here. And similarly, I have 2, which is a 0, 1, 0, so that's 3.3 and 0, and 3, which is 0, 3.3 and 3.3, and so on. And I'm just gonna write one more, 4, which is 3.3, 0, and 0, and so on, all the way up to 7, which is all 3 bits are on, 3.3, 3.3, and 3.3. So we'll calculate how our V out is. So first I'm going to do an analysis for one of these. So let's do a analysis of our 4. So the circuit for this situation is, we have a 3.3 here, a 0 here, and a 0 here, which gives us an equivalent circuit. I'm going to draw the equivalent circuit here, which is our 11K with a 3.3, and we have these two which are in parallel, and they connect to our 0 volts, and we want to find out what V out is. And V out is with respect to 0, so we want to find out this voltage. So if I were to convert this, and remember these are 22K and this is a 44K. So if I were to convert this, the equivalent circuit looks like this, where I have 22 times 44, remember these are in parallel, by 22 plus 44, which gives me a value of 44 by 3 kilo ohms. Okay, so I have 44 by 3 here, and I have 11K. They're in series, and what I have is a voltage divider, and so I know that V out is going to be given by a value which is 44 by 3 divided by 11 plus 44 by 3 times 3.3, which comes out to be 4/7 times 3.3. So that's my 4/7 times 3.3. Now it's a good idea to do one where there are two of them that have ones. So let's take this example of 3, which says now my circuit is, equivalent circuit is going to be one where I have a 0 here, a 3.3 here, and a 3.3 here. So now I have this circuit, which is my 0, and I'm going to draw it this way. Let me clear it. So the equivalent circuit is this, where I have my two resistances, which are 22K and the 44K, which are in parallel with 11K, and 11K is at 0 volts, one end of it's at 0 volts. This is my 3.3 volts, and I want to find out what the voltage here is, which is my V out, which by the way is the voltage across the resistance 11K. So again, my circuit is similar because we already calculated it. So this is a 44 by 3, this is 11K, and this is my V out, and that's 3.3 and 0 volts. And so it's a voltage divider, but now my V out is given by 11 divided by 11 plus 44 by 3 times 3.3, which gives me a 3/7 times 3.3 volts, which is 3/7 times 3.3 volts. So similarly, we can fill in the rest of my analysis. So this is a 3-bit DAC using a weighted design.
So Professor Yarabali, what will they do in lab?
So in the lab, you will take this idea of the design and extend it to 4 bits, which means that you will add an extra bit, which is B3, and you will make a 4-bit DAC, which will be much better because it will be better at more levels, more precision, more resolution. Therefore, when we hook it up to a sound, you can produce really high quality sound.
Sweet.